The 1927 Nobel Prize in Physics is a little different than those that came before him. So when we've seen other prizes in the past where more than one person won, it was for what's called a shared prize, where people work on the same project together and win it for the exact same work. This was a divided prize, and that's not to say these two people necessarily hated each other, but it's a prize that was equally divided for two works, which were both considered to merit a prize. And in some cases, when you see a divided prize, they're coming at the same problem, just from completely different directions. And that's what we have this year, is a divided prize, not a shared prize. And it was divided between Arthur Holly Compton and Charles Thomas Rees Wilson. Now, Compton won it for his discovery and effect that was named after him. We'll get to that in a second. And Professor Wilson won the prize for his method of making the paths of electrically charged particles visible by condensation of vapor. So let's dig into what that means. So as we talk about the Compton effect, it's important to remember that electromagnetic radiation comes in all forms. It's FM, AM radio, the microwave oven, all kinds of the visible light coming from the sun. It's all electromagnetic radiation. And at the time, it was not widely accepted that electromagnetic radiation was purely a wave phenomena, but it wasn't widely accepted that it was both a particle and a wave. And that was something that was still being argued by the theory groups. Well, along comes Compton and says, well, I'm going to run this experiment, and it's going to prove to you that it actually has a dual nature. So in Compton's original experiment, the energy of an X-ray photon would come in, which is significantly larger than the energy that holds an atomic electron on. So the electron could be treated as being free after it was scattered. So the electromagnetic radiation of an X-ray comes in, smacks into some graphite. That graphite's going to release an electron, and that electron will go off with some predictability. And that predictability can be determined through math. You'll have to know the original wavelength, the resulting wavelength, some of the regular Planck's constant, which was discussed in another Nobel Prize, the electron mass, which again was discussed in another Nobel Prize, the speed of light, which thank you, Professor Einstein and others, and then we find that scattering angle. Boom. So you can actually figure out where to put the detector to pull these things in if you run the right set of mathematics. And Compton was the first to really run this and see this, to say, hey, look, guys, it's not just behaving like one, it's actually both, which is where we get that duality of light, which applies to all electromagnetic radiation. Now, I promised to talk about the other winner of this prize, Charles Thomas Rees Wilson, and how he came at the same problem from another direction. So he was a much different type of physicist than was Compton. He was actually a physicist as well as a meteorologist. And what he did was, he was a Scottish gentleman, and he invented this thing called a cloud chamber. And what he was trying to do was study clouds and how they form, and so we could understand them better and maybe use that to predict the weather a little bit better. But what he quickly realized is that if you introduce ionizing radiation into them, you get these little streaks through the cloud. And that streak is very dependent upon exactly what type of radiation you ran through the system, and that gives you the very same, not the very same information, but it gives you similar information to Compton, and in that it will let you see that duality of electromagnetic radiation, so you can see the dual wave particle nature in streaks through the cloud inside a system. And this was actually the original cloud chamber, which is still at the Cavendish Lab in Cambridge, England. So both people got to the same answer. Look, we found two different ways to see that dual particle wave nature of electromagnetic radiation, but they came at it from very different directions. And that's why this was a divided instead of a shared prize. Thank you very much for tuning in again. If you haven't yet, there's a bunch of other Nobel Prizes discussed on the channel, and over time we will finish out the physics prizes, move on to chemistry, and then the other disciplines. Don't forget to click like on the video and subscribe, and if you want to hit the bell icon, you'll know when new ones are released. If not, the playlist always has them for you. We are starting a new show that will talk about more modern topics in physics and how they apply to our lives every day. So we'll see you soon.